So here's another question, which is the combination of conservation of energy and projectiles. And these kind of questions mostly is quite hard, but if you do it step by step, it should be fine. So first, let's have a look at the question first. A ball of mass 0.4 kilogram is struck by a bat at the point O, which they already drawn it for us, which is 1.12 meter above horizontal ground. The unit vector I and J are respectively horizontal and vertical. Immediately before being struck, B has the velocity of this, and immediately after being struck, it has velocity of this. So first, I need to write down U is equals to minus 20I plus 4J, and V is equals to 15I plus 16J. So this is the reason I picked this question, because it includes impulse, vectors, conservation of energy, and projectiles, which is kind of a real mechanics question. After B has been struck, it moves freely under gravity and strikes the ground at the point A as shown in figure 3 that it's drawn for us. The ball is modeled as particle. Okay, so it's really important that the ball is modeled as particle. I will explain that later. Okay, so first we do A. Calculate the magnitude of the impulse exerted by the bat on B. We know that impulse is equals to m v minus u, which is the change in velocity. So m times v, which is 15, 16 minus 24. And I really like to do question with vectors, because in vectors they already give you the direction, which is the negative, positive, so I don't need to care about the positive and negative sign anymore. So here we know that m, which is the mass, is 0.4. So 15 minus minus plus, which is 35, 15, 12. So J is equals to 14I plus 4.8 J. Since they want us to find the magnitude, so we can't leave our answer as a vector form. Okay, so we know that the magnitude of impulse is the square of 14 squared plus 4.8 squared. So 14 squared plus 4.8 squared, square root, we get 74 over 5, which is 14.8 Newton second, with 3 significant figures. Next, by using the principle of conservation of energy here, or otherwise, find the speed of B when it reaches A. So here it says or otherwise, which means you don't need to use conservation of energy to solve this problem. So that is just a suggestion for you. So find the speed of B when it reaches A. So where's A? Here. Here we can use conservation of energy. So first, we know that this ball has gravitational potential energy, and since it's moving with a velocity, so it has kinetic energy. After it reach A, it won't have gravitational potential energies because it's already on the origin, but it will have kinetic energy. So here we know that GPE initial plus kinetic initial is equals to the kinetic energy during the final. So mgh initial plus half mv squared is equals to half mw squared. Okay, here you will notice that why I don't use u and v, because I already used u for velocity before it get hit by the bat. So which means this is v, this is u. So I can't use v for the velocity at a anymore, because it will cause confusion to the examiner or other people. So I need to put it as w for the velocity. So we can cancel out m, left with ghi, which is 1.2 plus half v squared. We can find the magnitude of v squared by doing square root 15 squared plus 16 squared and square everything equals to half w squared. Okay, so if we square a square root, the square root will be gone. So we're left with half 15 squared plus 16 squared, which is 481, equals to half w squared. Multiply both sides by 2, 2.4 g plus 81 to w squared. So w is equals to square root 12613 divided by 25, which is 22.5 meter per second. Since I used g, so I put my answer as 2 significant figure. Done. Okay, now C. Calculate the angle which the velocity of B makes with the ground when B reaches A. So here, which means we need to separate this W into two separate components, because the velocity W will form an angle with the ground, which is theta. So to find this angle, we need to use the trigonometry. So here, since we have W, so we need to find either the horizontal component or the vertical component. Here, I will find the horizontal component, and I will show you why. In projectile, we always assume that there is no air resistance. So the component, which means the horizontal velocity, will always be constant, since there is no air resistance. So the acceleration will be 0. Since we know that the horizontal velocity for the ball is 15I, which is the horizontal component, so we know that the horizontal will be 15. So here we can use cos theta is equals to 15 divided by W, and W, which is square root 12613 over 25. So theta will be 15 divided by 668. So theta will be 48.1 degree. In here, by using trigonometry, you actually simplify the calculation a lot, because a lot of people will try to find the vertical component, which is quite complicated, and I won't say it's complicated, I would say it's long, and it's really easy to make mistake there. So the last one, D. State 2 additional physical factors which could be taken into account in a refinement of a model of the situation, which will make it more realistic. So what can we say about this model? First, as I said just now, we ignore the air resistance. So in real life, air resistance will always exist. So here we can say there will be air resistance. Okay, the second thing, which will definitely happen in real life but not in this model. Here, the ball is modeled as a particle, which means the ball does not have dimension, which means it doesn't spin, because when the ball spins, it's actually cause a rotational effect on it, so the value will be different too. So in real life, the ball will actually spin, so the ball will spin. Okay, so this is two additional physical factors that we can write down in the refinement of the model. So that's all for this video, and I hope you learned something from it. If you learned something, please leave a like and subscribe to my channel, and I will see you in the next video.